Hello, I hope you are all doing well. In this lecture, we dive into the pool of probability. We want to know why probability distributions are important. Then we'll be talking about how we can calculate the probability density function, probability math function, and cumulative distribution functions for three distributions. We mainly focus on uniform distribution, normal distribution, and binomial distribution. Now, here we have an important question. Why probability? Last time, we simulated a random walk process. We just used the random module, and then we generated 1,000 instances. Technically, we simulated the process of tossing a coin, and then based on the result, then we assign +1 and -1 to a variable. So why random processes and stochastic processes are important, and probability distributions are the main building block. So here, the question, there are a few options. So because we like probability and that's why we want to study it, or we use probability concept in a statistical analysis, which can be valid, or probability distributions help us with modeling uncertainty in processes, just like a random walk process. All of the above, or maybe none of them. So I do believe that we use probability concept in a statistical analysis, and we can use the probability distributions to model uncertainty. Random walk as one of the examples. Also, Monte Carlo simulation is a great application of probability distributions. When we have lack of data, we can use probability distribution to generate thousands of instances. And then with Python or other modules, we can calculate probability, we can measure the performance of the system, and study the behavior of the system. For example, if uniform distribution can be assigned to a process, then we can generate several. We just need to identify two parameters, upper bound, lower bound, then we generate several instances, and then we treat it as our data set, and then we can analyze it. So that's why probability distributions are important. In this lecture, we are going to use SciencePython library, which is one of the core libraries in Python, which can be used for scientific computations. It also has stats functions under this library, which provide us with a large number of probability distribution and statistical functions. So here, stats refers to that module under a SciPy package. Stats.distribution.rvs or random variables generate random numbers from the specified distribution. The argument to RVS or random variables will vary depending on the type of the distribution you are working with. If you are working with a uniform distribution, we need two parameters, A and B, upper bound, lower bound. If you are working with a normal distribution, we need two parameters, mean and standard deviation. Or if you are working with exponential distribution, we only need one parameter, lambda. We can also calculate the cumulative distribution function when the probability of x is less than or equal to a value. Stats.distribution.cdf is used to determine the probability that an observation drawn from a distribution falls below a specified value, known as the cumulative distribution function. So CDF also gives the area under the distribution density curve to the left of a certain value on the x-axis. So if you remember from a statistic for continuous random variables, the probability of x less than equal to a is equal to the integration of that function, and it technically returns the area under the curve. A stats.distribution PPF is the inverse of CDF. It means that it takes the probability and then it returns the x value or the cutoff value associated with that probability. A stats.distribution.pdf is a probability density function, which gives that probability height of the distribution at a given x value. We are going to see a few examples when we apply these functions. Let's start with the uniform distribution. As you may know, the uniform distribution is a probability distribution where each value within a certain range is equally likely to occur, and values outside of the range never occur. So the domain of the variable is between A and B, lower bound and upper bound. Density plot of a uniform distribution is flat, so it's like a box, because no value is any more likely than another. So they are all equally likely. Here you can see an example. We generate some uniform data and then we plot a density curve to see if we see that flat curve. First, we import scipy or sciencepython.stats, and then I assign a nickname as stats. We are going to use pandas as a data structure and also use the matplot library just to plot the result. First, I define a variable named uniform underline data. So I call my stats library, then .uniform, this is the probability distribution, .rvs. Then we pass 3 arguments. So how many random variables? Here, 10,000. So for this probability distribution, we need 2 parameters, location and a scale. Location is the lower bound here, and a scale is the upper bound. So uniform distribution between 0 and 10. And anything outside of this interval is 0. Then I define a data frame using pandas. So I assign the uniform data to this table, and then I use the plot function, density. We define the x-axis limit, so if we want it to be between -1 and 11, and then we show the result. Let's implement this in a notebook, and you can see what the results look like. So first we need to import the libraries that we need. One is sciencepython.stats as stats. So we use this library to generate different probability distribution and random numbers. Then we import pandas as PD. Then we import our visualization library, matplot library. And we use this for visualizing the random walk process. I assign a nickname, PLT. And let me first run these 3 lines, and now we can generate the random numbers. Uniform underline data. So first we use the stats library, uniform distribution to generate random numbers, RVS. Then we pass 3 arguments. So we want 10,000. Lower bound location is 0. Upper bound scale is 10. And now we want to assign it to a table. So we call it data pandas.data frame, and then we print to see what the result is. And then we pass the uniform numbers. So uniform underline data. Let's print data. So you can see that it's a table with 1 column and 1,000 rows. Then I call this variable. I apply the plot function. The type of the plot is density. The limit on x-axis is between -1 and 10. And then we want to show the plot. Let's run this. So this is the density function. First off, it's defined between 0 and 10. And you can see that it's almost flat. And anything outside, let me change it to 11 so you can see. anything outside of 0 and 10 is 0. So in this example, we use the stats library, and also we use plot.density to visualize the result. Now we can calculate CDF or PDF for uniform distribution. Stats.uniform.cdf, so we can find the probability of x less than or equal to something. So we need to pass the value. Let's say x is equal to 2.5 and two parameters for uniform distribution, location 0, scale 10. And in this uniform distribution, there is a 25% chance that an observation will be in the range 0 to 2.5, and a 75% chance it will fall in the range 2.5 to 10. If you apply the PPF, we need to pass the probability, and it's this example, it's Q equal 0.4. If we want to know the cutoff value for which we have a 40% chance of drawing an observation below that value, we can use the PPF. So let me implement this in Python so you can see. Stats uniform, and let's say we want to see the PPF, which is the inverse of CDF. So we pass the probability and then parameters for our distribution. Then if we run this, you can see the cutoff value is 4. So the probability of x less than or equal to 4 is equal to 0.4. You can change it if you change the range from 2 to 10, and then you get another value. Now, if we want to calculate density function, so since the uniform distribution is flat, all x values within its range will have the same probability density, and x values outside the range have a probability density of 0. So we want to print this. So let's in this example, we are using a for loop to generate numbers between -1, 12, and the step value is 3. First, we print this string density at x value, and then we return the x value, which is in range. And then we call the stat function. We apply the PDF at x with range 0 and 10. So let's implement this, and we expect to see same probability density, right? Because it's the uniform distribution. Everything is uniformly distributed. So for x in range -1 and 12, the step value 3, we print this statement. Density at x value plus a string, so we pass the value of x as a string. Then we print the result of stats.uniform.pdf at x, such that location is equal to 0 and scale is equal to 10. So let's run this and look at the result. Density at value -1. So the range of this function is between 0 and 10. So anything outside of this range should be 0. So for -1, we get 0. But for 2, 5, 8, we get the same probability, 0.1, 0.1. And 11 is also outside of the range, so its density is 0. This shows the behavior of a uniform distribution. The second probability distribution we are going to talk about in this lecture is normal distribution. Normal is a continuous probability distribution characterized by a symmetric bell-shaped curve. A normal distribution is defined by two parameters, its center or mean and a spread or a standard deviation. So we need to pass two parameters. The bulk of the observations, the majority of observations generated from a normal distribution lie near the mean, the exact center of the distribution. Now, as a rule of thumb, if we calculate the total area under the curve, about 68% of the data lies within one standard deviation of the mean. So the probability of x between -1 and 1 is 68%. 95% lies within two standard deviation. So the probability of x between -2 and 2 is 95%. And 99.7% lies within three standard deviation. The SciPy nickname for the normal distribution is norm. So in this example, we generate normal instances and we apply the CDF function. So this the output shows that roughly 60% of data generated by a normal distribution with mean 0 and a standard deviation 1 is below -1. So technically we want to verify what we just said. Okay, the total area is 60%, when the total area is 68% and 95%. So it means that we need to calculate the probability and we can use the CDF. So I define three variables. The first one, as you can see here, is probability under -1. So I call a stats, the nickname for normal distribution, which is norm, and then I apply the CDF. The value is the probability of x less than or equal to -1. So x is equal to -1. And then we pass two parameters for our distribution. This is the standard normal distribution. So local is equal to 0 and the standard deviation is equal to 1. Now we want to find the probability over 1. So the probability of x greater than 1. We can look at the event complement. So it's equal to 1 minus the probability of x less than 1. So we prefer this format because for probability of x less than 1, we can apply the CDF. So this probability is equal to 1 minus CDF at x equal to 1. Now, if we want to find the probability between these two, we add up the probability under -1 and over 1, and then we subtract this from 1, which returns the probability between -1 and 1. And then we print the output for these three variables. Let's try to implement this in a Python notebook. So three variables. The first one, probability underline under -1. We call the stats function, stats module norm, and then we apply CDF function. X is equal to -1 because probability of x less than or equal to -1. Location 0, scale equal to 1. Okay. The other variable, probability of over 1. Oops. Which is 1 minus the probability of x less than or equal to 1. X is equal to 1, the same parameters, location equal to 0, and a scale equal to 1. Between underline probability is 1 minus the summation of the past value, so the probability of underline minus 1 and the probability over 1. Now we can print the result. Make sure we don't have a typo. I'm going to copy and paste the variables here, comma, okay. Now I can run this and we can see the result. The probability of x less than minus 1 is the same as probability of x greater than 1 because normal distribution is symmetric, and the probability of x between minus 1 and 1 is almost 68%. So with this example, we applied the CDF function and calculated a few probabilities. And we showed that 68% of observations lie between -1, 1 standard deviation in a standard normal distribution. Now we can discuss the binomial distribution. So when we were talking about the random walk simulation, so we flipped a coin, right? Now if we repeat that experiment 100 times, 10 times, or 20 times, then we are dealing with a binomial distribution. This distribution is a discrete probability distribution that models the outcomes of a given number of random experiments. It means that we know how many times we want to repeat that experiment beforehand. 10 times, 100 times, or 20 times. The binomial is defined by two parameters: the probability of success in any given trial and the number of trials. So if you consider the case of flipping coins, the probability of success, if it's a fair coin, is 50%, and the number of trials can be 10, 15, 25. The binomial distribution tells you how likely it is to achieve a given number of successes in n trials of the experiment. For instance, we could model flipping a fair coin 10 times with a binomial distribution, where the number of trials is set to 10 and the probability of success is set to 50%. In this case, the distribution would tell us how likely it is to get 0 hits, 1 hit, 2 hits, and so on. So the SciPy name for binomial distribution is binom. So now we can call the stats library binom and then apply the CDF, and we can calculate the probability of x less than or equal to a value. The CDF function lets us check the probability of achieving a number of successes within a certain range. So here you can see two examples. We pass 3 arguments. First, the value k equal to 8, if we want to find the probability that we observe 8 successes, such that we repeat that experiment 10 times and the probability of success is 80%. For discrete distribution, like binomial, we use the probability mass function. So for continuous random variables like exponential and normal distribution, we have probability density function. But for discrete distributions, we have probability mass function. So that's why we use PMF to check the mass or proportion of observation at given number of successes. So the probability that x is equal to 5, we see exactly 5 successes, then we use the PMF. But if we want to see at least 5 successes, then we can use the CDF. Now let's implement this. A notebook, a stats, binom, CDF, let's say we want to find the probability we see at least 8 successes, n equal to 10 and p is equal to 0.8. So you can see that probability is 0.62. Now if we just change the value of k, if we pass k equal to 5 with the same parameters, then that probability, you can see, is really smaller. And if we want to find the probability mass function, k equal to 5 with same parameters, 10 experiments, and probability of success is 50%, then you can see the probability that we observe 5 successes. We can try for another value. When k is 8, n equal to 10, and p is equal to 80%. And then you can calculate the probability. Now, to wrap up our discussion, I have a couple of practices for you, and we want to answer these probability questions using the CDF or PDF functions. It also gives us some context. So electrical engineers recognize that high neutral current in computer power systems is a potential problem. A survey of computer power system load currents at US sites found that 10% of the sites had high neutral to full load current ratios. So that's how we collect data. Sometimes we collect data through surveys. Now, if a random sample of 5 computer power systems is selected from the large number of sites in the country, what is the probability that exactly 3 will have a high neutral to full current load ratio? To answer this probability question, we need to identify what distribution we are dealing with. So first, we are taking a sample of 5, and then we want to know the probability that exactly 3 will have a high neutral to full current load ratio. So other words, we are looking at the number of successes. If we define the success as a high neutral to full current load ratio, then we are dealing with the binomial distribution. So I can use the stats library, binomial, and use the PMF or CDF. I would encourage you to pause the video and try to answer these probability questions and then compare your answers with mine. So in part B, we want to find the probability that there are at least 3 sites with a high neutral to full current load ratio. So we have a sample of 5 and we are looking at least 3 successes. In part C, we are looking at less than 3. So we need to pay attention to this to calculate the right probability. So for exactly 3, it means that we are looking at the probability when x is equal to 3. In that case, we can use the probability mass function. But when we are dealing with at least or less than, we use a CDF function. That being said, let me implement this in a notebook. So the answer for part A is stats.binom. We are using PMF because we are using exactly 3 successes. K is equal to 3. We have 5 samples and the probability, so 10%, as you can see here, 10% of sites had high neutral to full load current ratio, and that becomes the probability of success. If you run this, you can see it returns the probability of k or x equal to 3. Part B is at least 3. So we are looking at the probability of x equal or greater than 3. So we can use the event complement. In other words, that probability is equal to 1 minus the probability of x equal or less than 2. So a stats.binomial CDF when k is equal to 2 with same parameters and p equal to 0.1. So that probability, first we calculate the probability of x less than or equal to 2, and 1 minus that probability is our answer. Part C, we are looking at less than 3, the probability of x less than 3. So this is a discrete random distribution and 3 is not included. So it's the probability of x equal or less than 2. So we print a stats binomial distribution CDF where k is equal to 2, n is equal to 5, and p is equal to 0.1. And you can see that probability is almost close to 1, 0.99. The last question, suppose that y is a normally distributed random variable with mean 10 and a standard deviation of 2.1. We want to find the probability that y is equal or greater than 11. So if we want to find this probability, we need to transform this into a standard normal distribution and use the tables that we have in the back of a statistic book. But here, by using the CDF or PDF functions, we can find that answer using one line of code. So the first one is the probability of greater than 11, which is equal to 1 minus the probability of y less than or equal to 11. And then the second question is to find the probability that y is between two numbers. So let's try to answer the first one first. So it's the 1 minus the probability of x less than 11. It means that we can use the CDF function. So a stats.norm CDF where x is equal to 11, location is equal to 10, and a scale is equal to 2.1, the standard deviation. Then that probability is equal to 0.31. Now to answer the second question, first I calculate the probability of y less than or equal to 7.6. Then I calculate the probability of y less than or equal to 12.2. Then I take off the probability of y less than 7.6, and that would be the result. So I define two variables, A is a stats.norm.cdf, the probability of x less than or equal to 7.6, where location is 10, a scale is 2.1. And that probability is 0.12. Then I calculate the probability of x less than or equal to 12.2. Stats.norm.cdf x equal to 12.2, location 10, scale equal to 2.1. I assign it to B. That probability is 0.85. Then the result is B minus A. That's the probability that we are looking for, 0.72. And with that, I wrap up our discussion about probability distribution.